Right, so it's 11 o'clock. I'm going to go ahead and get started now. So welcome to the new norm for the rest of the semester, everyone. So I imagine a lot of you have tons of questions about like homework, tests, how the rest of the semester is going to work. And I will get to those questions, but I'll ask you guys to hold off on those until we get through this lecture. I've got I estimate about an hour's worth of material that I just want to get through because I want to get back to doing physics, to be perfectly honest. So we're going to talk about magnetic fields and do a little recap, a summary of them, and we'll go on from there. So any questions about like how the rest of the semester is going to work, I'll ask, please hold that till we get through the material I want to cover today. All right. So I ended the last lecture, which was weeks ago now, asking about how to make uniform fields. So let's just dive right in. I'll repeat that a little bit. I started by asking, how do we make a uniform electric field? Right. What device do we use for an electric field? And that was the parallel plate capacitor. We'd say, take two charge plates, they have different charges, and that would automatically generate this nice, constant electric field through them. So the question became, well, how do we make a nice uniform magnetic field? Right. What are the tricks we're going to do there? We know that we've been playing with wires. Take a straight wire, have some current going through it, what kind of magnetic field that's going to do. And that'll be some rotating circular one. So we're going to take the things we've played with before and just try and postulate. And we'll start off with a current loop. So I'm going to take my loop of current, and I'll send a current this way around, counterclockwise. Right. Now apply your right-hand rules. There's two of them, I'll go through both, right? You can do the grabbing the wire trick, right? So if you grab the wire, what we're going to do is your palm's the wire, palm's grabbing the wire, your thumb's direction of current, and your fingers curl in the direction of the magnetic field. So I find that inside this loop, I have magnetic field coming out of the page. Right? Now, if you prefer the universal right-hand rule, right? Let's see, mu naught. This is a magnetic field for a long straight wire. Right? And we talked about my universal rule. How do I get the direction of the field? So the wire, or the magnetic field, that'll be your thumb. The current is your index finger. Make this legible. And that R is your middle. The R means the distance from the wire. How far away from the wire? So in this example here, let's have a current. Right. Here's my current. I want to know the magnetic field a distance r away. Right. So I have my wire current. I have a distance r. R is how far away from the wire am I? And then say, what's the magnetic field? So try my universal right-hand rule. Index, direction of current. Middle is R. Middle is pointing direction. My thumb says out of the board. And so you do this along the whole length of the wire, and you find magnetic field that is there's my magnetic field rotating along the long straight wire. Well, let's apply this principle to figure out the field back in the loop, right? Because remember, the goal, what we ask ourselves is, I want to make a uniform magnetic field. My long straight wire, right? As I get further and further away from the wire, as R increases, that magnetic field goes down. We try it for now just a single wire, right? Remember your right-hand rules. Grab it or right-hand rules. Direction of current. I'm going to look inside the wire, inside the loop, magnetic field. So inside here, I have magnetic field coming out of the board. So natural question is this nice and uniform? Not quite. It's not uniform yet. Remember, the closer I am to the wire, the stronger the field. So if I was really close to the wire, it'd be a nice, strong dot, big field. And as I get a little closer, as I get closer and closer, the field shrinks down. So what we have with the loop, with one loop we have same direction, but it's not the same strength. All right, can you guys make out, is that too tiny? I'm going to assume that's a yes.
I mean, it's more so the quality of the video than the size of what you're writing.
Okay, okay. So is the writing at least legible? Because I know there's issues with this. Okay. Now I'm gonna keep going. All right. So point. One wire, okay, one current loop got me a field that's always pointing in the same direction, but it's not the same strength. Go for a 3D perspective of that. Right. Right. 3D perspective of the single loop. Right. What these fields are doing is so we're going to have to try something else. And it'll be related to this. Right? Try stacking tons of loops on each other. Don't have just one loop. Right? Have multiple loops stacked on top of each other. well, then you get better and better, right? You get the field right? By stacking multiple loops on top of each other, we're getting the field more and more uniform. And so we say a solenoid creates uniform magnetic field. Right? A solenoid is composed of N loops of wire all stacked on top of each other. All right, so N loops of wire, they'll have the same current, some current I, and has a length L. So here's my wire that's N equals 4. 1 loop, 2 loop, 3 loop, 4 loop. All right. So there's my 4 loops. 1, 2, 3, 4. I'll say there's a current coming in this way, and that length L refers to how wide, how long is my solenoid.
I have a question.
Yes.
All the way on the right, you have a capital N is equal to, or is that greater than something else? Underneath N loop is, what does that say?
So this is just an example. Just drawing just one solenoid with 4 loops.
Oh, 4. Okay. Okay.
Right. So, what's the magnetic field of our solenoid? Right. B solenoid is going to be mu naught, the number of turns over the length, I. That's our magnetic field in a solenoid. Now, your textbook and tons of resources, they like to rewrite this. They like to define a little n, a lowercase n. Right. They like to define what they call a lowercase n. Some resources will call it a number density. And then they'll rewrite this as mu naught little n over I. Let's make that a little bit clearer. Right. So these two expressions, they are equivalent. They are the exact same thing. It's just a lot of people like to get lazy. They don't want to think of there are 4 turns over 5 centimeters. They're just going to say, how many turns per centimeter? That's what this is. The number of turns per unit length of wire. And so depending on the problem or what resource you're looking online, they'll jump back and forth between these. So what I'll say is just a warning, don't, when like you're working on that homework or working on tests that I know you're all thinking about coming up, don't just blindly say, I see a number, plug it into this formula. You have to ask, what's the unit of the number? What makes sense unit-wise? Right. So let's do a little practice problem. Right. I'm going to have two solenoids. I'm going to call them solenoid A and B. Right. Right. So solenoid A is 10 centimeters long and carries, let's see, carries a current of 1 amp. So it's 10 centimeters long, 1 amp, and has 500 turns. So I'll help highlight this. 10 centimeters, 1 amp, 500 turns. Now I'll take my second solenoid, solenoid B. B is going to be 20 centimeters long. Let's see here. 1 amp of current. And this guy will have 1,000 turns. Right. So visually, I always like to put a picture to this. So visually what we're looking at is, here's A. Right. B is going to be twice as long and have a lot more turns. So just make a right. Right. A and B, both of them carrying 1 amp of current through it. So the question is going to be, how do their magnetic fields compare to each other? How does BA compare to BB? How does the magnetic field strengths compare? All right. So let's just calculate one of them first. And I've given us all the information, no tricks here, so we can just plug and chug. It's mu naught N over L I. Right, mu naught. That is the magnetic permeability constant. 4 pi 10 to the minus 7th Tesla meters per amp. Right. Times N over L. So N for coil A, 500 turns. 500 over the length, 10 centimeters, which is 0.1 meters. Multiplied by the current, 1 amp. All right. Let's see here. 4 pi times 500. What's your 4 pi? I see a 4 times 5, 20 pi. Factors of 10. I've got 10 to the minus 7th. I've got 2 factors of 10 here, 1 factor of 10 here. Stitching all that together, you'll find it's 10 to the minus 4th.
Excuse me, what is the unit of U naught?
U naught?
Yeah.
I'm going to squeeze it in down here. So the units of U naught is a Tesla meter, not enough space. Tesla meter ampere. So magnetic field, length, current.
Gotcha, thank you.
All right. All right. So where was I at? Magnetic field of A. Oh, we got the 20 from doing 4 times 5, pi's lying around, and then we just counted up powers of 10 to get that was 10 to the minus 4th. Right. If you plug this into your calculator, worked it out, you would find it is 6.28 millitesla. Right. Good tight. So now let's do the calculation for the B field. I don't know how A compares to B, so let's just plug things in. BB. Well, it's going to be U naught. We are going to be clever. This one was 500 turns. This one was 1,000. So I'm just going to say 2n. Same trick for the length. If this was 10 centimeters and this one was 20 centimeters, I've doubled the length again. So I'll just call this double L. Same current. Oh, 2 over 2 cancels out. U naught in, there if it helps. You have those subscript A's. A over LAI. Turns out it's the exact same field. So to walk us through the physics, I took this coil, I stretched it out, I made it longer, and then I filled the gaps with twice as many turns to replace what I lost. And so by doing that, I kept the same field. Right. Question coming, or are we just getting noise? I feel like there's a question, so I'll pause.
There was a question in the chat about where the, I think, micro Tesla came from. MT?
Millitesla. Okay.
Millitesla?
So where'd that come from? All right. I'm going to erase the right board. Right. So, right. Let's go back here. This is 20 pi 10 to the minus 4th Tesla. Right. 20 times pi, that's basically 20 times 3. Number-wise, that is 62.831. So 20 times pi is 62.831, yada, 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 whatever. right? Shift this down by -3 to turn into millitesla. So 62. I'm just gonna keep the first decimal. Let's see here. This is 10 to the -4th. I'll just rewrite as millitesla. Let's see here. This is, let's see here. More space. 62.8 10 to the -4 Tesla times. There is 1,000 millitesla in 1 Tesla. So that becomes 62.8 to the -1 millitesla, 6.28. So I was just playing with the position of tens. All I really care about, honestly, is this one and any permutation. Like, I would accept this, I would accept this. Like, I don't really care. There's the physics. All right.
Understood.
All right, let me catch up on the chat. Let's see here. All right. So for those of you in the chat, just a heads up, I can't see the chat in my current setup. So next lecture, I'll take that into account. I'll try and get the position of my computer, right? So I can try and see your chat. All right. Where were we? Let's keep going. All right, let's try another one. This will be, all right, multiple choice. Here's my setup. I'm gonna have a solenoid. I'm gonna have wire coming out of the page, out of the board on top. So it goes out, then in, out, in, out, in. And I'm gonna have myself a little battery to provide current. And then we'll put a bar magnet here. Right. So the question is, when I turn on this current, there's a magnetic field being produced in the solenoid. What direction does the permanent magnet move? Right. And I'll make this multiple choice. Right. It can go to the left, it can go right, or it can go in or out of the page. So left, right, into page, I guess board, so we need to figure out the direction of magnetic field. And to get that, we gotta go with the current. So you start with saying, well, what's the current through that solenoid? Once I have the current, what's the magnetic field? And then when we have the magnetic field, we finally can ask, where's this guy gonna go? So, current, let's start there. The current in this guy, positive, negative, current's gonna go, and conventional current is gonna go from the positive lead around to negative. So there's current, goes up, and then, well, what's this perspective? I said out, in, out, in. Let's try and redraw that, right? We'll make it a little less confusing. I said at the top, it's coming out. Here, it's coming out towards you. At the bottom, it's going in. So our current's doing this. Out, out, out. There's my solenoid currents, right? Out, in. Now do your right-hand rules, right? Right-hand rule. If I do this right, I'm gonna go with the x's. So my x says, I guess, I'm trying, right? I'm going with the x's. So I'm gonna have a magnetic field, I see your current. What? All right, I see your question, Stephanie. It's in the picture setup. So direction of current from the battery, we'll start there, positively going around. Here, it's the geometry of the solenoid. And the diagram has to make it clear. If not, like I have to convey what it's doing. So it's kind of hard to draw this 2D perspective. Let me try drawing this again. Let me try drawing it from a different perspective. We'll go a 3D drawing of this. That's not clear. One more time. It's gonna be coming. Here's my battery. And then over here is my bar magnet. Right? So follow the current, right? I'm gonna go this way, around, around. And then I'm at the top of the loop. At the top of the loop, I come out. At the bottom, go in. And then repeat. Top of the loop, I'm coming out. Bottom, coming in. Out, in. Right? So I'm following the wire. The wire is telling me from this 2D perspective. What the current's doing. All right, excellent. So now I've got what is the current doing from just a slice, right? Think of taking that solenoid and just slicing it in half and looking at it dead on. Now I've got my currents. Let's get the magnetic fields of the solenoid. So I'm gonna go with the bottom one, right? I'm gonna use my universal rule. So bottom, right? Direction of current. I wanna find the field that solenoid produces. So X's, I'm gonna go to the bottom. I'm going into the board. Where am I measuring the field? That's the middle finger. Where am I measuring the field? Well, I'm going to measure inside the solenoid. So I'll repeat this. All right. Direction of current. I'll go with the bottom side. Direction of current goes in. Where am I measuring the field? In the middle. Direction of magnetic field, my thumb. That's the direction the solenoid's producing. Right? Plenty of other ways to convince yourself of that. You go with the top of the wire, right? So if I go to the top of the wire, if I go to the top of the wire, current's coming out towards you. Magnetic field. Sorry, guys. Magnetic field, I want to measure inside the solenoid. Direction of magnetic field, there's my thumb. Right. Another way, if you prefer the grabbing the wire technique, let's go with this one. If you prefer grabbing the wire, right? I don't want to say this. I'll see the bottom of the wire. I see current going into the board, so I grab it, measure inside the field. So it doesn't matter where I grab the solenoid, I'm always going to find the field going to the left. Or, sorry, to the right. Field's going to the right. So let's come back to this picture. We can put in the magnetic field of this guy. All right. Now I got to pause and think for a moment. I have a magnetic field that's going that way. Does that look like a magnetic north or south? Basically, does this guy feel attracted or repelled by this arrow?
Repel.
I'm hearing some repels. I do see some attraction. I'm going to erase the options. Right. So let's look at just the bar magnet. Let's center this guy. Right. So a bar magnet, the fields, you know, go around like so. They say, whoop, and they come out of the north into the south. So the north end of the magnet sees fields going out, away from it. So coming back to this picture, this solenoid sees the magnetic field coming that way. I'll draw it this way. Here's my solenoid. Here's my magnet. There's a solenoid's field. We can say it looks like, just put a north magnet here. It looks like this. I'll do it in yellow. This is fictitious, but it gets us the picture. So a permanent magnet can make a field like that by being oriented this way. So as far as this magnet is concerned, what does it see? It sees the north end of another magnet. So go back to the original question. Which way does this guy move? Left, right, in, out?
Right.
Gotta move to the right. It's gonna be repelled away. So it moves to the right. Hopefully. All right. So I'm going to keep at this. I've got another problem of just writing this out. I could write for days about the theory behind all this, or we could just do more practice problems. So I've got another one, and unless anyone objects, I'm going to clear the board and try another problem. Right.
Is the current always flow from the south to the north?
What baby? Okay. Good question. Let's try this one again, and I'll change things up. So let's take this guy. Same thing. And I'll switch the direction of the battery. Great. So I flipped the direction of the battery. I've flipped the direction of current. So now current does this. And then let's see here. I get careful. So I said the wire goes out here. I said it's going out the top. The wire goes out the top. Wire's coming out, in, out, in, right? Comes out, in. So here it's coming out, out, in, out, in, out, in. So then in that case, I would have current out. So in this case, when I flip the battery, I got the same field back. So that means I need to flip the solenoid to get a different result. So if I flip the solenoid, so instead of coming out the top, right?
Is it going to look the same when you draw it?
I'm going to try and make it look different, but I think it's going to look the same. I got to be very careful.
Okay.
Yeah, so just a warning, the trickiest part of these problems is making that diagram as clear as possible. It's actually, as you guys start to notice, tricky. So I'm gonna I can hear the thoughts coming through the internet. On a test, if this comes up, the wording will be explicit. Like I will say like into out of the board, like I'll make it very explicit, or I'll have the picture be, I'll draw it this way. Here's another way. Instead of looking from the side, looking dead on like this, I'll draw the perspective as if we're looking down here. So picture will look like this. Let's see here. I said into the board at the top. And then here's our magnet, north to south. Let's minus. All right. So kind of hard to tell. So let's put our eye here. Right. So we're going to redraw this looking straight down, and what do we see? We see this. Right? Current's coming out this way. Therefore, it loops around like so. So this is the equivalent to that picture on the right, but just looking on the edge, looking basically down the solenoid. I guess my water bottle's a prop, but so you can think of it as, here's the solenoid. You guys cannot see that. So imagine this is a solenoid. Right? So here's my solenoid, and then the picture on the left is me doing that. And you see this perspective again, right? So all I'm doing is taking the object, and rotating my view. Now, hopefully this one's a bit clearer. The magnet's way off down at the end, and I say, what's the direction of magnetic field of this loop, right? I guess technically it's a solenoid. Magnetic field. So I go with, let's go for the top of the wire. At the top of the wire, I see magnetic field going that way. I want to know the magnetic field inside the loop. I see magnetic field coming out. Let's go back to my prop analogy. Right. I have magnetic field coming out in this picture. So let's go back to the drawing on the right. If I take this in, rotate it that way. You see magnetic field coming towards your eye. All right. Check on chat.
So for this one, you didn't flip the battery, but you flipped the solenoid.
Correct.
Okay, thank you. In this case, it will be attraction?
Correct. In this case, in this picture, yes, the north sees a magnetic field going away from it. North says attract, come towards it. So this case would be attraction.
Thank you.
All right. I'm going to reset. And we're going to try new type of problem. Same type material. Right. We're going to step away from solenoids and just say, let's add up magnetic fields. So I'm going to have my two transmission lines, two wires. Right. Wire one's doing this, carrying some current of 74 amps. Wire two, right? This one's carrying 27 amps, right? These guys are separated by some distance d. They're separated by 38 centimeters. And I'm going to put a little coordinate system here. So So X positive that way, Y is positive that way. All right, so the question is, where is the net magnetic field 0? So this breaks into basically 3 categories. You can have above wire 1, in between the wires, or below the wire 1, or below wire 2. So you've got 3 regions. Above wire 1, B, between the wires, or C, I'm saying the sum. Where is the sum of the magnetic field 0? Easiest way to do it, don't do any math yet, right? We focus on pictures, we focus on drawings. So I'm gonna give these colors. I'm gonna make the top wire blue. Right. And now let's find the magnetic field of just the blue wire. So direction of current, let's go above the wire. I see magnetic field coming out. So this guy does field coming out. Now if I look beneath the wire, right, direction of current, I go beneath the wire, thumbs coming in. So this says magnetic field into the board, keep going down, it's still just into the board. Now do the same thing for the second wire. All right, we'll give this guy a color code. Right. Same trick, right? I go direction of current, above the wire, I see magnetic field out of the board. And obviously below the wire. I go below, in. All right. Where's the net field 0? I need wire 1, right? I need wire 1's going one way, wire 2's pointing the other way. I need them to be, I think that actually visible. I need the direction of their fields to cancel, to be opposing each other. So if I look down here, into the board, they add up. They keep supporting each other. Up here, out of the board, they keep adding up. They're keeping the field going away. It's only in the middle, somewhere between the wires in this picture, right? Going back and thinking of like the solenoid, can I flip the currents or flip the wires? Yes, I can arrange this such that any one of these regions is correct. It just depends on the geometry of the problem. For this problem specifically, it works out that in the middle, the field will be 0. Great. So now the problem is position so I want to find the height, right? Let's redraw this a little bit. Right. I want to find the height some y value I want to find the height above this wire where that net field is 0. That's the goal. So I'm going to erase this in the middle now. All right, nothing in chat yet. I'll draw this again. So we're going to have current 1. Here's current 2. Here's my axis, positive x, positive y. There is some height, R2 equals y. R1, right? When I say R2, R1, what I mean is R2 is the distance from wire 2. R1 is the distance from wire 1. Right? So I label this as D, at 38 centimeters. Before we even continue on with the math, this distance y, right? Should it be, if this gap is 38 centimeters, half of that gap, half the 38 is 19 centimeters. Should I expect y to be more than half the distance or less than half the distance between the wires? All right. All right, I saw one answer in chat claiming it should be smaller than. Absolutely correct. Absolutely. It should be smaller. How do you know this? Without doing any of the math, it comes back to the currents. This guy is 74 amps. This guy's 27 amps. This guy's making a huge magnetic field. This one's making a weaker magnetic field. So in the line between them, we know that the distance needs to be closer to this wire, because as you get further and further away from a wire, the field strength goes down. So we got to be closer to wire 2 so that their respective fields can still kill each other. So when we finish this problem, when we go through all the work, our answer better be smaller than 19 centimeters. Otherwise, we know we screwed up. Let's do the math now, right? So B net is going to be B1 plus B2. I'm trying to find where it is 0 Tesla. Right. I'll bring 1 across. Minus B1 equals B2. Right? We're not worrying about vectors. We only care about the magnitudes. So I'm just saying, when is the strength of B1 equal to the strength of B2? When that equation is satisfied, we have found whatever the heck this Y value is. Right. 74 amps, 7 amps. Erase this. Right. Let's start filling in. The magnetic field for a wire, B wire, is U naught I1 2 pi R1. mu naught I2 2 pi R2. Just setting the field of one wire equal to the field of the other wire. All right. We've got some nice cancellation. Magnetic permeability constant out. 2 pi's. They're out. So we can cancel those terms and we're left with just this ratio. I1, R1, I2, R2. Right? Remember, R's, these say the distance from the wires. I'm trying to find this Y thing. Go back to the picture. We already labeled what R2 is. R2 is that height Y we're trying to find. So I'll rewrite this one. What we're trying to solve for. R1, I need to rewrite it in terms of this separation, that 38 centimeters, and the Y, the height above wire 2. So you go D minus Y. Right. R1 can be expressed as 38 centimeters minus the height we're trying to find. Right. No questions yet. Right. I'm going to leave the middle board and erase the right board. Right. Solve for Y, right? I've got a Y here, got a Y here. I want to know what Y is. I1, I2, numbers, D, 38 centimeters. I know everything but the Y's. So let's just solve for it. I'll multiply Y across. I'll multiply D minus Y across. So I'm going to get a Y I1 is equal to I2 times D minus Y. Just getting the stuff in the denominator out of the denominator. Cross multiplying. Y1 equals I2D minus I2Y. I got Y and Y. I'm trying to solve for that. I'm going to bring this guy across. Y1 plus yi2 is equal to I2D. Right? Factor out the y's. Y I1 plus I2, I2D. Write it out. Divide this and I get I1 plus I2 all over I2D. Let's not erase anything. Yeah, I suspected that. So I am going to pause.
Okay. All the way on the right side of the screen, the second equation. Yes. How did you get D minus I2Y?
Multiply this out. I2 times
Oh, okay.
I2 times Y.
Got it. Okay.
All right, so I'm gonna stay paused here for a second. There's more questions on the algebra that we just did. All right. So
And then below that, I see yi1 plus yi2. Where did the yi2 come from? Above that.
I took this term.
Mm-hmm.
I took this term and just added it across.
Oh, okay. Got it. Okay. Sorry. It was a lot going on at once.
That's fine. That's fine. So yeah, just I got all the y's on one side of the equation.
Is a unit of D meter?
What baby? D is this separation at 38 centimeters.
Does that have to be converted to meter in the equation?
Okay. Good question. Let's come in the middle. So the answer is, for this particular problem, it doesn't matter, right? Current divided by current, dimension, unitless. So the units on amps cancel out. And so whatever answer you plug in for D will be the units for Y. So do you want Y in meters or centimeters? That's basically what we're asking now.
Okay, gotcha. Thank you.
So yeah, so let's plug in the numbers. I'm not gonna leave you guys hanging on just that. Right. So I2, I said it was 27 amps all over, let's see here, 74 plus 27 all times, and I'm just going to do centimeters because I don't care if Y is in centimeters for at least this problem. All right. 74 plus 27 is 101. Amps, the units cancel out, so 27, 101 times 38. Space, okay. Right. So this is approximately 1/4. This is about 40. I won't waste your time doing the approximation. We'll just actually straight up do this calculation. This is 10.2 centimeters. So before we started all this algebra, I asked, should this answer be less than or greater than 19, less than half the D? We said less than. Hey, look at that. 10's less than 19. Our math checks with our physics knowledge. All right. Let me find a way to get out of the way of the board. Right. So, any questions along this chain of events of drawing pictures, doing a bunch of algebra? All right. So, can you pause for some? Nope. All right. Well then, with the remaining 5 minutes of our lecture time, I'm going to do just a brief recap of this entire magnetic chapter, right? So I'll erase the board again and start filling it up. This is going to be just a quick review, okay? All right. So to start off for our review of magnetism, right? All right, force on a charge in a external B field. That is, FB is QVB, sine of the angle between the velocity and the magnetic field. So a great picture of this. If I have magnetic field in this picture going into the board, and I fire in a positive charge going that way, the force on this charge, right? Direction of velocity, direction of field. This charge has to feel a force in the upward direction. Make that a little bit louder. Right. Continue on. If I have not just a single charge, but if I have a length of wire and magnetic field. So force on a current wire in an external D field. So I'm saying, here's my magnetic field again. And let's shoot a wire. Let's shoot my wire in there. The force on that will be ILB sine theta. What is L? L in this picture it is the length it's the length of the wire that's in the magnetic field. That's what L is in that expression. All right. Keep going. So we need to make sure to distinguish between these guys were forces. Oh, drafted a force. Current of wire, magnetic field. This guy's also feeling a force pointing up. Right. So we need to distinguish between the fields, the forces on a wire versus the fields that wire produces. Remember, guys, think of the units. If there's anything I'll always emphasize, remember what is the physical quantity. So, switching from forces on those wires to fields these wires make. Magnetic field of a current carrying wire. U naught I 2 pi r. If this is my current, it makes a magnetic field like this, going around it, where r is the distance from that wire. All right, we'll get out of the picture. So that was my short 4-minute recap of this chapter. Honestly, didn't cover everything, but I hope it reminds you of all the key stuff that we need to remember. And with that, I'll call an end to this lecture.